All right, so these are some of the practice problems, or actually some of the review questions from 9.3. So for this first one, you have to arrange some bonded pairs from least polar to most polar. So here I've listed them out, and the first thing we need to do is find the delta or the change in electronegativity, so to do that, we're going to take the most electronegative value and subtract the least electronegative value for each bond. And so I'm just writing down those values now. All right, so here I've written down the values and I've subtracted them all. So we need to remember that anything with a difference of less than 0.4 is going to be nonpolar. Anything between 0.4 and 7.1 is going to be polar. And anything greater than 7.1 is mostly ionic. All right, so now I've identified each one as being ionic, polar, nonpolar, and so what I would do then is, since we're going from least polar to most polar, then we would most likely start with the lowest number. In this case, that is the pH bond. And then you would have the chlorine-fluorine bond, and then you would have the bromine-carbon bond, and finally you would have the aluminum nitride bond and the potassium oxide bond. The next part, we had to determine molecular geometry and decide if it was polar or nonpolar. So for this one, I'm just going to do 3 examples. Carbon bromide or carbon tetrabromide. So we know we're going to have a carbon and 4 bromine atoms. We know that each of these dashes represents 2 electrons being shared. So we've already used 8 electrons, and we haven't even counted how many we have. So we know carbon has 4. We know that each bromine is going to have 7, and there's 4 bromines. So all total, we have 32 electrons we have to count for now. Like I said, we've already used 8. So we're going to put 6 on each bromine. That uses up a total of 28. And so, or 24, and then 24 plus the 8 we started with, that leaves none left for lone pairs. So we have 4 bonding pairs, and we have no lone pairs. Okay. So no lone pairs. And so then when we look it up, we can see here that with 4 bonding pairs around it, it's tetrahedral. All right, so the next thing we have to do is decide if it would be polar or not polar. All right, so just like we did in the first problem, we can look at the structure, and we're going to look at the difference in electronegativity. So the structure is a tetrahedral. So it would be something like this with carbon in the middle. And when we do the math, we're going to end up with 296 minus 2, or 2.96 minus 2.55, which is 0.41. So this would be almost nonpolar. It's just barely by 100th of a point in the polar range. But all of the points of this tetrahedral would have the same charge. It'd be slightly negative. So this would be nonpolar. All right, moving on to dihydrogen sulfide. All right, so we know sulfur is going to be on the inside and the hydrogens are always on the outside. And we also know that hydrogen can only make one covalent bond. So we put one pair between each hydrogen and the sulfur. Now let's do some math. Hydrogen is going to have one valence electron and there's two hydrogens. So, all right, and the sulfur would contribute 6. So we have a grand total of 8 valence electrons. So I have a mistake here on my paper. So we have 2 bonding pairs and 2 lone pairs with this structure. So then once we know that, we're going to have to look back at that chart. But we have to look at the chart that includes lone pairs. So here you can see that we're talking about tetrahedral with a bent geometry. Now, water is polar because it is bent, but will that work out for dihydrogen sulfide? All right, so let's crunch some numbers. So we have 2.20 for hydrogen and 2.98, 58 for sulfur. So that gives us 0.38, which is less than 0.4. So each hydrogen sulfur bond is non-polar. That's going to make the molecule as a whole non-polar. All right, so now we have boron trifluoride, or maybe this would just be boron fluoride. So we have 3 boron, or 1 boron, it has 3 valence electrons, 3 fluorines with 7 each. So we have a total of 24 valence electrons. We've already used 6 of them, and there are 6 more, and 6 more, and 6 more. We have now used all 24 valence electrons, and so we've used them all. There's no lone pairs. So to figure out the geometry, we can look back at that diagram. And so we see that this would be trigonal planar, which would mean it makes kind of a triangle shape, but all of the atoms are in the same plane. There's no perpendicular ones. Okay. All right, so now we crunch some numbers. We have 2.04, and we're going to subtract that from the 3.98 for fluorine. That gives 1.94. That is way over 0.7. So this is an ionic bond. And so the answer key lists that as nonpolar. So that's what we're going to put it as. Now for this last part, you had to tell which one would have the higher boiling point. And so we have ICl or Br2. The molar masses of these are about the same, but we see that ICl is polar, so it's a dipole-dipole bond. Br2 is diatomic and nonpolar. All right, so ICl is going to have a higher boiling point because of those dipole-dipole intermolecular forces. And then HF is going to have a higher boiling point than HCl because of hydrogen bonding. So here we have ethanol and dimethyl ether. Both have the same formula, C2H6O. But the boiling points of ethanol is 78 degrees, and the boiling point of dimethyl ether is negative 25 degrees Celsius. So why is this? And the answer is basically hydrogen bonding. Ethanol has hydrogen bonded to oxygen, so it can form hydrogen bonds.